I'd like to welcome today for our colloquium Professor Tomas Karlsson, coming from Sweden, from the University of Technology, KTH in Stockholm. So Tomas is a long-standing, actually officer, I was going to say, but a long-standing collaborator of us. He's been working with a lot of different missions that we've been interested in, that we work with here at the Institute. That's Martin Volverk and Tomas go a long way, especially. So we just a few words about Tomas. So Tomas did his PhD a long time ago in another galaxy, I guess, on black aurora, and then started to work quite a lot with magnetometer data on both these missions all across the solar system. So he's working with MMS, he's working with solar orbiter, GSP, a lot of different environments, Venus Express as well. So connected to a lot of those subjects is actually the topic of today, which is the magnetic holes in the heliosphere and planetary magnetosheaths. And then we will learn to understand a little bit what those strange depressions in the magnetic fields are and why they are like that and how they change from the sun towards the outer solar system. So Tomas, the floor is yours.
Thanks, Cyril. Okay, first of all, when I have a mixed audience like this, I want to know how many of you are not plasma physicists? Raise your hand. So to get everyone on the same page, I will begin with my 1 minute to bring that to speed. I'm sure many of you are familiar with plasma physics since you've heard a lot of stuff from all these other plasma physics. But anyway, a plasma is an ionized gas showing what we call connected behavior. That's only a way of saying that we have to have enough ionizations that the gas now can exhibit electromagnetic phenomena in addition to the ordinary gas dynamics. And we can create the plasma by heating a gas, or we can shine ultraviolet radiation on it, which is actually what happens on Earth's ionosphere, where the sunlight ionizes the upper part of the atmosphere. Or you can throw particles at the gas, like in the aurora, for example. Now, in space, we very often have a magnetized plasma. That means there's a magnetic field inside the plasma. And when you have charged particles in a magnetic field, they will feel the magnetic force, which is all the time perpendicular to the velocity of the particle and the magnetic field. So this creates this gyration around the magnetic field. Here it's illustrated by an ion and an electron rotating around the magnetic field. So the plasma particles are stuck on the magnetic field lines. So that gives many important, explains many important properties of a magnetized plasma. For example, the particles can now easily move along the magnetic field, but perpendicular to the magnetic field, they can only move a little bit, this gyro radius distance. So electric conductivity and heat conductivity might be much higher along the magnetic field than perpendicular to the magnetic field. And you can, for example, have different temperatures along the magnetic field and perpendicular to it. So what I describe now is what we call the single particle picture. We can also typically describe the plasma as a fluid, a gas, and there's a similar way to describe this magnetization. It's called the frozen-in field line theorem, which was one of the reasons why Hannes Alfvén from KTH got the Nobel Prize to show this. So if you have two plasma elements that on one time are stuck on the same field line, if what is called the magnetic Reynolds number, which is basically the conductivity of the plasma, is very high, those two plasma elements will stay on the same magnetic field line for the future, even if you move the plasma around and the field lines around like this. So that means you can typically see the plasma, the different plasma populations being stuck on different magnetic field lines in nature like this, like on this coronal loop on the solar surface, or in the northern lights, the aurora. And by the way, I always take the chance to ask when I talk about the aurora, how many people have seen the aurora? You're about average. Okay, now you're all plasma physicists. I want to just bring you up to speed a little bit on space plasma physics or space physics, just so we're on the same page. So as I'm sure all of you know, the sun emits not only electromagnetic radiation, but also a plasma. The sun is a big ball of plasma, and it points out the solar wind like this. You can see here, you see it's sped up, so it's 1 day approximately in this movie. And you can see this flow of plasma, and sometimes there are these ejections called coronal mass ejections. Now, due to the frozen-in magnetic fields in the in the solar wind drags out the magnetic field from the inner part of the sun out to long magnetic field lines that fill the whole solar system. We call this the interplanetary magnetic field. Now, this is again also kind of an illustration of this frozen-in field theorem. If you have a magnet and you have a superconductor, the magnetic field cannot penetrate into the magnet because of the high conductivity of the superconductor, and you can levitate a magnet like this. Something similar happens when the solar wind encounters the strong magnetic field of a planet like the Earth. This magnetic field cannot penetrate into the highly conductive solar wind. Here we forget about the magnetic field in the solar wind and just think of this as a superconductor approaching a magnetic field from the planet. And actually you can set up this magnetic pressure to balance the dynamic pressure of the solar wind. That gives you a balance, a force balance here, which is actually what happens when you form the magnetosphere of Earth or other planets. Solar wind has to go around the magnetic field, and it draws out the field lines on a long tail like this, creating a magnetic bubble inside this region, which we call the magnetosphere. And I will talk about a little bit later about some different magnetospheres in the solar system. And due to the different field strengths of the planets, and due to the different distance from the sun, and therefore the different density of the solar wind, there will be a large spread of sizes of these magnetospheres. So here's Earth's magnetosphere, tiny compared to Jupiter's huge magnetosphere. And you might wonder here, where are Venus, where's Mars? Well, those are slightly different because they don't have their own internal magnetic field, but actually because they have an ionosphere, again, the magnetic field cannot penetrate into this conducting ionosphere, so you have to hang up the magnetic field lines around the planet like this, creating something we call an induced magnetosphere that kind of looks a little bit like an ordinary magnetosphere. I just want to mention one final thing about plasma and space physics before we move on. I'm going to talk very briefly later about a process called magnetic reconnection, which I'm sure many of you have seen as well. So when you have these oppositely directed magnetic field lines and they come together, they can be cut up and reconnected in a new configuration like this. And in the process, you convert magnetic energy, you destroy some of the magnetic flux and convert that magnetic energy into kinetic energy of the plasma flowing out from this region. Okay. Now I think we're kind of on the same page, everyone. I will move on to talk a little bit about the main subject of magnetic holes. So what are these? From the solar orbiter mission. So what you see here is around 4 minutes of data in both plots. And if we concentrate on the top panel here, you see the strength of the interplanetary magnetic field, the solar wind magnetic field. You see it's typically rather quiet like this. And then suddenly you see these deep dropouts, what we call magnetic holes. These come in kind of two different flavors. I've marked them as linear and rotational here. What that means, if I plot not only the magnetic field strength, but the magnetic field components like this, you see on each side of the magnetic hole, there's not a big change in the direction of the magnetic field. It points in approximately the same direction here as here. Whereas, so we call this linear magnetic holes, they are linearly polarized. Now, if you look at this one over here, you see there's a big change in the magnetic field direction from one side of the magnetic hole to the other. The magnetic field basically flips direction. So the magnetic field has rotated strongly from one side of the magnetic hole to the other. So we call these rotational magnetic holes. The magnetic holes have been observed already since the late 1970s by Turner et al. But still kind of mysterious things. We don't know exactly how they are formed and what their properties and effects are. One property that we do know about magnetic holes is that they are often found in pressure balance. That means the decrease of the magnetic field strength in this magnetic hole is there's a decrease of magnetic pressure. You remember, you could define a magnetic pressure like this. When you have a magnetic field, you have a corresponding pressure of the magnetic field. So the magnetic field decreases in this magnetic hole, but this is compensated by an increase of thermal pressure inside the hole. So the hole lives in pressure balance. You can see this in an example observation here from Stevens and Casper. You can see how the temperature and density increases to increase the thermal pressure, and you can see the total pressure remains about the same. The decrease of magnetic pressure is taken up by this thermal pressure. This was actually started by Martin using data from Earth from the MMS mission to see how often this thermal pressure was taken up by an increase of density versus an increase of temperature. And like you can see here, it's often a combination. So Martin found this general distribution. Sometimes it's the temperature mostly, sometimes it's the density, but most often it's a combination. So going back to our examples, we can actually see that happening here. And what I mentioned about this plasma balance, pressure balance, is mostly has been studied for these linear magnetic holes. And you can see the decrease of magnetic field here. The particle data are just about, you have the time resolution to see something. You can see there's an increase of temperature and density here in the magnetic hole. And actually the same for the rotational magnetic hole. We should go back and verify this statistically, that the same thing is true for these rotational magnetic holes as well. I don't think anyone has done that yet. Okay, so this is like a cut through a magnetic hole with one spacecraft. That doesn't tell us really how they look in 3 dimensions and so on. And one of my PhD students just recently, a few weeks ago, graduated, and she studied the 3-dimensional morphology of these magnetic holes using cluster 4-point measurements. Cluster are 4 satellites flying together in formation. And she used a simple model, Gaussian model, to fit the 4-point data when these spacecraft fly through the magnetic holes. And for this example event here, she concluded that this is an elongated ellipsoid, not quite rotationally symmetric. It's a little bit flattened, as you can see here. And she made a large statistics on this. This is around 400 different events. And she has presented it in this form. If you take this ellipsoid and you calculate what we call the planarity and the elongation, you can see what types of morphology these magnetic holes typically have. So you have a large planarity, that means the structure is kind of flattened like a pancake. And if you have a large elongation, as you can hear, these are elongated structures. And you can see most of the points end up here. So these seem to be not rotationally symmetric things, that either flattened pancakes or what we call knife blades, a flattened ellipsoid like this. So this is a little bit surprising. I think most people did expect the magnetic holes to look like this. And finally, for this magnetic hole introduction, how are these things created? Well, we don't know, but one of the leading theories is that they are connected to what we call mirror mode, the mirror mode instability, which is, I mentioned you can have different temperatures, perpendicular and parallel to the magnetic field. If you have a much larger perpendicular temperature, sometimes the plasma becomes unstable and you blow up this big balloon, magnetic mirror mode configuration. Mirror is called mirror because the particles will be mirroring back and forth between these strong magnetic field regions. And this actually, this can happen very often in regions close to Earth's magnetosphere, where they then are generated as a kind of wave-like phenomenon, like here. Our magnetic holes, the ones I talk about, they are all the time isolated. I'm just talking about these isolated magnetic holes, but they might be related to these mirror mode waves. Maybe these things die out, or they become very nonlinear and they can merge with each other. That's one theory, but that's one of the main theories, that they are related to this mirror mode instability. That's true for the linear magnetic holes. These rotational magnetic holes, they are believed to probably be totally different animals. They are probably related to this reconnection process, where you have a current sheath associated with this strong rotation of the magnetic field from one side of this current sheath to the other. I'm not going to talk about that much here. I just wanted to mention these are two very different types of things, the linear magnetic holes and the rotational magnetic holes. At least we think they are. They just happen to look very similar. Okay, now for my main theme today, I think, how do these magnetic holes look like at different parts of the solar system? In particular, I want to compare the inner and the outer heliosphere. So the way I'm doing that, okay, I'll give you a little spoiler here. This is basically my result. This is measurements from the Solar Orbiter spacecraft at 0.4 astronomical units. That's around Mercury orbit. And this is from the Cassini spacecraft from the cruise phase. This is a little bit outside of Jupiter orbit. And you can see in the close to the sun, they're very small, just a few seconds wide. Out here at Jupiter and Saturn, they're kind of like a half a minute wide. So this is the main result. They become larger the further out in the heliosphere you go. Okay, that's based on 2 data points. So let's do something a bit more statistical. But by the way, they are formed very close to the sun as well. We know that they can be formed close to the sun at least. This is, I think, a world record, I call it, from Parker Solar Probe, 15 solar radii out, less than 0.1 astronomical units. That's very close to the sun. Actually, yesterday I went through the newest data and I found one even closer. It's not as nice, so I want to show this one more. But it's really, really close. So, okay, let's do now this a bit more scientifically. Let's make a statistical investigation. I'm going to use data from the inner heliosphere from Parker Solar Probe and Solar Orbiter. Go from very close to the sun out to about 1 astronomical unit. And then I use the Juno cruise phase data and the Cassini cruise phase data to study the outer parts of the heliosphere. And I define a magnetic hole as a 50% decrease of a background magnetic field that I calculate by smoothing the background the IMF, interplanetary magnetic field, with a window of around 5 minutes. And then I take the difference, the delta, and see when that is less than 50%, I have a magnetic hole. And I only want to study these isolated magnetic holes. So if they're too close to each other, I throw them away. So then in the inner heliosphere, of course, we have many observations. I get around 5,000 events from Parker Solar Probe, 4,000 for Solar Orbiter, 800 and 600 respectively for the Juno and Cassini cruise spaces. So here are the first results, first way of presenting the results. These are the distributions of the temporal scale sizes, so just the thickness of these things. I use full width at half minimum to define the scale size. And what you see here is a kernel density estimates. That's a continuous form of a histogram, if you haven't seen it. Think of these as histograms. So in the inner heliosphere, Parker Solar Probe and Solar Orbiter, you see they have an average of 5 seconds around and a mean of 9 seconds. For the Juno data in the middle heliosphere, out to 5 astronomical units, mean is around 17 and median 13 seconds. And again, for the Cassini data in the outer heliosphere, you see the mean and median are around 40 seconds. So very clear trend, they become larger statistically, the further out in the heliosphere we go. So, okay, these were for linear magnetic holes. What about if I look at the rotational magnetic holes? I set a limit, by the way, when there's more than 40 degrees rotation across the hole, I call it a rotational magnetic hole. Very similar results. They're like 5, 6, 7 seconds in the inner heliosphere. Should be 9.0 here, around 10 seconds, and around, well, between 30 and 40 seconds in the outer heliosphere. So even if these are totally different things, probably, they behave the same way when you move out from the inner heliosphere out to the outskirts of the solar system. I present this in one more way. So this is heliocentric distance, so this is a 2-dimensional histogram where I've actually normalized each bin to 1 just to be able to see the cloud scale a bit better. And this is the logarithm of the scale size, the temporal scale size of the magnetic holes. And of course, I have a lot more data here in the inner heliosphere, so the bins become larger when I go further out. But you can see that this general trend, if you look at the maximum of each distribution in each bin, to increase out to 1, 2, 3 AU, and then maybe it kind of stabilizes at a certain scale size in the outer parts of the heliosphere. So again, linear magnetic holes, poorer statistics for the rotational ones, they're not quite as common, but a similar trend for them. Let me present this in 1/3 way, which might be a bit easier to look at. If I, for each bin here, take the median value and plot it as a function of heliocentric distance, I get something like this. Linear magnetic holes, first, see there's it's almost a linear increase in the beginning, and then maybe at 6, 7, 8 AU, kind of stabilizes, maybe even decreases a little bit. Similar for the rotational magnetic holes. Strong increase in the beginning up to maybe 5, 6 AU, and then a stabilization or even decrease of scale size with distance. And these are based on quite a few events. These are the number of magnetic holes in each bin over here. So the statistics are relatively good. So how do we explain this behavior of the scale size of the magnetic field? Well, I guess there are two main hypotheses. Either the magnetic holes are formed locally, maybe the magnetic holes we see here, they are created where we see them, and maybe it's the different parameters in the solar wind that decides what size the magnetic holes will have when they are created. Second possibility is that, okay, maybe all of them are formed in the inner heliosphere, close to the sun, and then they are convected away with the solar wind, and something happens to them as they go further and further out in the heliosphere. Let's see if we can test this a little bit. So let's think about this first alternative. They are created locally where they are observed or very close. If, like I mentioned, they are related to this mirror mode instability theory, which has been the main theory so far, then their scale size, according to theory, should be proportional to the ion gyro radius. Remember this radius that the ions make around the magnetic field as they gyrate around. And we can estimate approximately what the typical gyro radius is at different heliocentric distances. So I've plotted a typical curve for the gyro radius using certain temperature and magnetic field strength at different distances from the sun, which we know statistically. So if I look, for example, at 1 AU, that's at Earth, and 9 AU, that's close to Saturn, I get the ratio of these gyro radii of around 23. So if this gyro radius should determine the size of the magnetic hole out here should be around 23 times as large as the magnetic hole here at 1 AU at Earth. But in fact, if you look at the data, there's only a factor of around 5 between 1 AU and Saturn. So they don't seem to grow or increase in size as much as is predicted by this simple theory. So my tentative conclusion is magnetic holes are not likely to be produced locally. So I think it might be that they are changing as they move out from the inner heliosphere out in the solar system. One way we can understand that, I'm trying to understand how that works. And I've come up with a sort of a very simple sketch of a model of how that might work. So we know statistically how the magnetic field of the sun, the interplanetary magnetic field, we know how it changes with distance from the sun, statistically. And that gives a different magnetic field pressure as you move out. We also know statistically how the density of the solar wind changes with distance. All of this is, of course, just statistically, large variations. But we know basically it decays as 1 over r squared. That's because, I mean, a sphere expanding will have a shell, the volume of a shell will decrease as well. The volume will increase as r squared, and the density will then go as 1 over r squared. So we know what the perpendicular, we can calculate what the perpendicular pressure is when we know the density and the temperature, if we know the temperature. Now, okay, when I talked about this pressure balance, remember the pressure balance between the magnetic field and the pressure, I was talking about this perpendicular pressure balance. Now, okay, we know these things. We can now actually also, under very general assumptions, calculate how the pressure changes as we move out in the heliosphere. This is based on the conservation of energy and momentum, and also something called the magnetic moment. So these are some very general assumptions. So we can actually calculate how the perpendicular pressure changes theoretically as we go out in the solar system. So let's make a thought experiment here. Let's take a magnetic hole at, say, 1 astronomical units close to Earth over here. So you see you have this magnetic pressure associated with the magnetic hole, and we say they live in pressure balance when we observe them. Earth, for example, let's assume that here, so that the total pressure is constant from when you go from outside to inside the magnetic hole. Now I can take this theoretical model here and I can propagate the magnetic field strength and the perpendicular pressure according to what I expect, how I expect them to change as we move out into the solar system. Now the thing is that the thermal pressure and the magnetic pressure, they will change differently according to these equations. So as I move out, if I have these original pressures, they will change differently, and I will mess up this pressure balance. So that means this is now just a thought experiment. You think you take a small piece of plasma, move it, let it go out with the solar wind in the outer heliosphere. And what happens is then that the prediction is that the magnetic pressure inside this plasma parcel, inside the magnetic hole, will actually be smaller than the pressure outside. Okay, what does that mean? How would nature respond to that? Well, if there's a region now where there's almost a vacuum inside and you have a large pressure outside, of course, the plasma, the solar wind, wants to compress the magnetic hole. That doesn't sound right. We saw in the data that they are blown up. They get larger, not smaller. How can this be? Well, my scenario, which I have suggested, is this. This picture isn't great, sorry for the quality. But anyway, if you think about a magnetic hole like this red cylinder, and it's going to be moved out with the solar wind, being carried by the solar wind outwards, again, due to the fact that the magnetic field is frozen into the solar wind, and the fact that the sun is actually rotating, that means these interplanetary magnetic field lines will actually curve like a spiral like this. This is called the Parker spiral. And you see, if you look at how the magnetic field is directed with respect to magnetic hole in the inner heliosphere, you see that the magnetic field is directed kind of along this cylinder. And as the magnetic hole is moving out with the solar wind velocity, if you have a spacecraft here, and this magnetic hole passes the spacecraft, what you measure is this dimension of the magnetic hole along the velocity. So if originally the magnetic field is, or the plasma is trying to compress this magnetic hole perpendicular to the velocity, we won't see that. But on the other hand, you can imagine you have a tube of toothpaste and you compress it. Of course, the toothpaste wants to go out in the other direction. So this would actually increase the plasma pressure along the magnetic field. And along the magnetic field, there can be no balancing by the magnetic field. There can be no magnetic force along a magnetic field. So that this magnetic hole will then probably expand along this direction, along the magnetic field, which in here is the same thing as along the solar wind velocity. Now, as the magnetic hole moves further and further out, you see that the magnetic field direction with respect to the magnetic hole changes. So now if we look at this extreme case, for example, if the plasma now wants to compress the magnetic hole perpendicular to the magnetic field, that is now along the direction which we measure. We only measure along this direction, along the velocity of the solar wind. So at least I think the expansion rate will slow, and you might even get a compression when we get further out in the solar system. Kind of consistent with what we see. Originally here, we would see a compression perpendicular to the magnetic hole, which we can't measure, but that would lead to an expansion along B, along the velocity. So you get an increase over here. Further out, the magnetic field is more directed like this. The solar wind will now try to compress the magnetic holes back again. And maybe when you go this far out, there might be a compression that is larger than the need for the magnetic hole to expand. So you might even get this decrease in scale size. So I think this is a possible scenario. I'm not saying it's totally correct, but I think as a summary for this, I think that we see that the scale sizes increase with the heliocentric distance only out until 5, 6, 7, 8 AU. And it's not consistent with local generation. And the fact that we see the similar trend for both linear and rotational magnetic holes, I think is a strong suggestion that they are actually modified as they move out in the solar wind. And I propose, or we propose, that pressure dynamics in some form is the underlying mechanism for the increased scale sizes of magnetic holes. And as we could see, this even predicts maybe a small decrease of scale sizes at really large heliocentric distances. Okay, where am I on time? We still have some time. 15 minutes. Yeah. So this was like my main theme for this talk, but I also want to talk about another aspect of magnetic holes. Their effect on the magnetospheres. Because when these magnetic holes hit the magnetosphere, you might get some violent effects. So let's think a little bit about that. So for example, if we look at Mercury here, Mercury's magnetosphere, the magnetic bubble, where the magnetic field is dominating inside this bubble. Actually, what happens when the solar wind encounters the magnetic field of a planet is that, first of all, before it really interacts with the planet, it breaks down from supersonic to subsonic velocities, just like a supersonic airplane creates a shock in front of it. So this creates this bow shock, which is a rather violent short region where the solar wind is suddenly break down and heated, and there's a lot of turbulence behind this bow shock. In this region, we call the magnetosheath, which kind of covers the magnetosphere. So the first thing we need to know is, can magnetic holes cross this bow shock and really interact with the magnetosphere? We want to think about how magnetic holes can interact with the magnetic environment and the space environment of the planet and perhaps change it. So first of all, there's some indirect evidence that these magnetic holes can cross the bow shock. This is from a study I made of the magnetic holes close to Mercury with the MESSENGER spacecraft. So these are some examples of magnetic holes which you see outside of the bow shock, out in the solar wind over here. And I won't go through the details here, but you can just see visually what they look like. And then inside the magnetosheath, after the bow shock, inside this region, before they interact with the planetary magnetosphere, they look like this. I would say very similar. Of course, the magnetic field is stronger in the magnetosheath because everything is compressed, but the size and shapes of the magnetic holes look very similar between the solar wind and the magnetosheath. And in fact, statistically, all of their properties are very similar, in particular their temporal scale size, which you should expect being the same if you cross the bow shock. The magnetic hole crossing the bow shock will be compressed and maybe deflected, but the temporal the time it takes for this thing to cross a spacecraft will be the same in both the solar wind and the magnetosheath, even if the flow velocity changes here. You can think of it as distance between two buses. If one bus starts 1 minute before the other, it's a temporal change of a difference of 1 minute between them. And that remains even if they hit traffic. And maybe the first bus hits traffic first and moves very slowly. The other one catches up with it. But there's still 1 minute between the two buses. So there's still 1 minute or 2 seconds or whatever between the front and the end of the magnetic hole in these situations. And here you see the distributions of temporal scale sizes in the solar wind and the magnetosheath for the magnetic holes we observed. So they're very similar. And all their other properties are also quite similar. So I think that's indirect evidence that you can see these isolated magnetic holes in the solar. It's just a mathematical formulation of the bus theorem I gave you. It's based on the one-dimensional continuity equation. So indirect evidence, but we also, as scientists, we like direct evidence. So this is another study I made of magnetic holes, now again using the cluster spacecraft. So I looked at situations where at least one of the spacecraft is situated here in the solar wind, and at least another spacecraft is situated here behind the bow shock in the magnetosheath. So here's an example. Here's a model of the bow shock in one projection of a coordinate system. And you see this red one, spacecraft 2, is out in the solar wind, and spacecraft 3 here, the blue one, which is actually sitting on top of spacecraft 4, is just inside the bow shock in the magnetosheath. And you can see the spacecraft 2, the red one, sees a nice magnetic hole over here. And a few seconds later, the solar wind has blown this structure across the bow shock. And you can see a very similar magnetic hole inside the magnetosheath behind the bow shock. They look very similar. You can even see this little substructure here. You can recognize it here in the observation behind the bow shock. I won't go into this. This is just some details of how these magnetic holes are expected to change when they cross the bow shock. But you can see even if their depth has changed a bit, you see the size is very, very similar. And I have a number of these cases, so don't worry, I won't go through all of them in detail. I'm just going to pick a random one, maybe this one. And you can see here's the observations in the solar wind and the observations in the magnetosheath. There's a lot more turbulence and wave activity in the magnetosheath, but you see this magnetic hole over here, which I plotted over here, looks very similar. So I think this is smoking gun evidence that the magnetic holes can cross the bow shock and enter the magnetosheath. And again, if I plot some of their properties for the solar wind observation for each magnetic hole versus the magnetosheath observation, you can see their properties in this case. In this case, the rotation of the magnetic field across the magnetic hole is conserved as you cross the bow shock. Okay, it's an outlier there, but in general, I think that's convincing. Same again for this temporal scale size. It seems to be conserved as you cross the bow shock. So at least there's some subpopulation of magnetic holes that can easily cross, or easily can cross the bow shock and come close to Earth. So I think we can now begin to start to investigate how these magnetic holes can affect the planets, the magnetospheres, and the space environment. Here's actually a very early try from a colleague. This is an MHD simulation of Mercury magnetosphere with a magnetic hole here in the solar wind. This is courtesy of Léa Breton. And you can see there are some, okay, it's not so easy to interpret this, but you can see there are clear effects when this magnetic hole enters the magnetosphere. Okay, like I said, this is a first try. I can't say too much about this, but this is the kind of study we can do with simulations, trying to understand how the magnetosphere is affected. And in particular, I'd like to show this old picture by Joseph Lemaire, in which his point was slightly different. But my point is that maybe we should move from this picture of a very smooth solar wind interacting with the magnetosphere to a picture where you have lots of different small-scale structures in the solar wind. There can be magnetic holes, there can be magnetosheath jets, like Savas here has studied, for example. And I think this is an important aspect of solar wind magnetosphere interaction, this non-steady interaction or non-uniform. There are some examples here which have been cited as effects of these magnetosheath jets. I think we can have very similar effects due to magnetic holes. We can set up different types of plasma waves on the bow shock and the magnetopores. You can then create perhaps strong field line currents closing in the ionosphere, modifying the ionosphere, injecting particles into the ring current, for example, or even creating auroral emissions. Okay, I'm getting close to the end. I just want to, when we talk about this interaction with the magnetospheres, I just want to make a very simple thought experiment again, to think about how different is this interaction for the different magnetospheres. And I'm basing it on a very, very simple thing. I'm just taking the size of the magnetic hole, typically at the different distances from the sun that we've seen, we studied statistically, and I'm comparing that to the size of the magnetosphere. So if the magnetic hole is small compared to the magnetosphere, the effect is probably going to be smaller. And if I just take a measure of the size of the magnetosphere, I'm taking what we call the subsolar distance, the standoff distance, the distance between the magnetopores here on the day side towards the sun to the center of the planet. I take that for the different planets, so I take the relative size of the magnetic hole to the size of the magnetosphere, and I've plotted it for the different planets here, Mercury, Venus, and so on out to Saturn. And we see for Mercury, the size of the magnetic hole can be typically well a good few 10% of the magnetosphere. So we should have a considerable effect. Of course, they become smaller the further in we go because of the sizes of the magnetospheres. And out in the outer system, solar system, these huge magnetospheres are probably not going to be affected much. But the case of Mars stands out because the Mars magnetosphere is quite small and the magnetic holes have reached a relatively large size at the Mars orbit. So I'm going to summarize very quickly. We see magnetic holes come in two different flavors, linear and rotational magnetic holes. Both of these types are seen over the whole magnetosphere. My interpretation is they are likely created in the inner heliosphere and convected outside as they and as they do, they grow to larger sizes. And I think these magnetic holes, among other structures, can represent a new type of solar wind magnetosphere interaction with particular importance for the inner rocky planets. And then I'm done.
Thanks, Tomas. Any questions?
I have a beginner's question. You, in your model, you had your magnetic hole moving radially, whereas the magnetic field was following this Parker spiral.
Yeah.
I just wonder why isn't also the hole following the magnetic field? Why is it strictly radial?
The density the energy density of the plasma in the solar wind as it moves out is several orders of magnitude larger than the magnetic field energy density. So it's always a question where you have these frozen in field lines, who is the master and who is the slave? And for the solar wind, it's very clear that it's the solar wind plasma that is the master and the magnetic field just has to follow. And that's true, I think, even inside the magnetic hole. There's enough, typically enough. It's not the thermal pressure that's important here, it's the dynamic pressure of the solar wind.
So all the particles go out more or less
radially out.
In the,
has to follow.
yeah, okay, because often in my science it's the other way, yeah. So that there's a magnetic
for the
field
nature of the energy.
and the flow has to curve when the
Yeah, that's true on the solar surface, for example. That's most of the time their magnetic field stays still. Plasma has to follow the magnetic field.
Is there a relation between the number of magnetic holes and the solar cycle? I mean, are there more holes than the
That's a very good question. We haven't checked. I should take my database and check that. I don't think, my guess is there will not be, but we should always check. I think there might be a relation between the fast and the slow solar wind.
Yeah.
And in that way, there might be an indirect relation to the solar cycle. Yeah.
Thomas? Two questions. So you said it's mainly driven by the solar wind pressure, right? So my question is, did you find any correlation between the size of the magnetic hole and over plasma parameter, like density and so on? And would this stretch of size not be due to the solar wind? So if you have like a distribution of velocity over time, like the slower gets slower and slower, so you stretch over time or over distance.
We should go back and redo all these things. From my preliminary checks, I don't think there might be some, again, indirect effect. I think this distribution is very clearly affected mainly driven by the heliocentric distance. But around these means, there's of course a distribution. And the way that distribution looks like, that might be affected about the things you mentioned, perhaps.
And my second question is maybe naive, but are there any data from Voyagers or Pioneer probe which could be beyond?
I've tried to look, but these old missions, the quality of the data is, we're so spoiled nowadays. If you go back and look at the magnetic field data Voyager, it's typically like 10-minute resolution, and there's an hour of data, and then there's a 20-hour data gap, and so on. So it's very difficult.
Well, thank you so much for this talk, in particular.
Thank you.
Stating clearly what is written on your axis. So I totally appreciate that. So I also have a couple of questions. And I'm coming from an exoplanetary background, being interested in the interaction between ionization, clouds, whatever is around. So we actually begin to understand what's going on and have to always ask very clearly, what is the background?
Yeah.
So therefore, you speak about magnetized plasma, and I would wonder at what degree of ionization you consider plasma to be magnetized.
Well, those are two different questions. I think the degree of ionization says something about, is it a plasma or not? And the degree of ionization can be quite small for it to be a plasma, just a %.
That's why we all are plasma physicists.
Exactly. It's just that you don't talk about it so much typically.
Okay.
But then once you have a plasma, I think almost the whole galaxy is what I would call a magnetized plasma.
Right. Okay. So then we are also totally magnetized. Then you have used the magnetic Reynolds number to speak about frozen in magnetic fields. Now I'm curious, there is a characteristic length in there.
Yeah.
You must assume something. And
That's the typical length of variations of the magnetic field in this case, because the derivative of the magnetic field, or the second derivative, will actually give rise to diffusion that breaks this frozen in theorem. So these are the typical scale sizes of things in the solar wind. And they are typically scale sizes of thousands or millions of kilometers.
okay,
And in order for this to be frozen, breaking down, you have to go down to maybe kilometer scales. So
Okay. Then I have a very naive question. On your, you had the slide where you showed the linear and rotational magnetic poles, and both seem to have, yes, this one. And if I simply look at the value of the magnetic field flux, I suspect, it's on the left-hand side for the linear, it's 3 nanotesla. No, the top level, the top one, and yes, this one. And the rotation is 4 nanotesla. Is there some depth in this, or is this
no, these are just examples. These are probably from close to 1 AU for orbit, where the magnetic field typically has this strength.
Okay.
But if you go further into the solar system, you see magnetic field strength are now a few hundred nanoteslas. So this is just a measure of where you are approximately. Of course, there's a lot of variation, but statistically speaking, this is where you are.
Okay, thank you.
Any more questions? Maybe one more question. Or comment? Okay, so I can,
This one there more.
it was, yes. Okay.
Was this also observed, for instance, in the ionosphere at low Earth orbit?
No, I have not seen anyone talk about these things in the ionosphere. I've seen magnetic holes being reported in the magnetotail of Earth, but not in the ionosphere. I could imagine maybe at Venus they might do it, might make it down into the ionosphere, because there the ionosphere is very close to the bow shock and the magnetosheath.
So I think I just want to say a comment. So thank you very much for this talk. And I think what we've seen also is that the cruise phase of satellites, when we launch them into space, is actually super important, because we can actually do science with also the cruise phase later. And so the magnetic holes is actually one brilliant example of that. We can use like these kind of long stretches of inactivity of the space mission to do some relevant actually science.
Yeah, right. They probe regions where we don't usually go.
Exactly. So I think that's something that Martin and Ruby actually discussed also in at conferences and stuff like that. Anyway, so I would like to thank one last time Tomas for his brilliant talk.